Chapter 2, slides 13 to 41. This is probably the start of one of the very important chapters in the first semester of organic chemistry, because I like to say that when I ask the question why in this course, there's a top 3 answer list to this question. Typically, students want to say that the reason something happens or the reason something is because it's more stable. And although that's pretty much the case, I would argue that that's not a complete answer. You could say it's more stable because ... Well, what's the reason for the stability? Why did it go to something that was more stable? What's causing it to be more stable? And one of the top 3 answers in organic chemistry is this topic right here called resonance. Now, resonance means a little something different when it pertains to, say, what you learn in a physics classroom. But resonance has a very important role when we're looking at structure, function, and reactivity. So we are going to use everything we've learned up to this point to understand how to recognize resonance, how to represent resonance, and what it means to the molecule. So drawing lines between atoms, as we've been doing with bond line structures, can be a little bit inadequate in certain cases. Let's take a look at this 3-carbon atom below. Carbon 1, carbon 2, carbon 3. What you'll notice is that as drawn, there's a double bond between carbon 1 and 2, and there's a carbocation or a plus formal charge on carbon 3. Now, understand that every first bond between 2 atoms is a sigma bond. So the bond between 2 and 3 is a sigma bond, and the bond between 1 and 2 is a sigma bond, and that extra bond that makes the double bond must be a pi bond. Now, I'm not going to use the orbitals to show the overlapping sigma bonds, but I'd like to hone in on the pi bond between carbons 1 and 2. And that's the 2 electrons being shared, and they're being shared in orbitals that are adjacent to one another and overlapping. So those are the unhybridized p orbitals we talked about in chapter 1. Those 2 red electrons for the pi bond are being shared by parallel unhybridized p orbitals. Now, if you take a look at carbon 3, if you see that it's just got a positive charge, you now know that there are 2 assumed hydrogens there, and it is lacking an octet, thus giving it a positive charge. Carbon 3 is an sp2 hybridized atom, which means it has 3 sigma bonds around that carbon that are using the sp2 hybrid orbitals, and it has 1 remaining p orbital available, and that p orbital is empty, and that's where we have our charge. So there is a p orbital at carbon 3, and that p orbital is in line, parallel with the 2 p orbitals that make up the pi bond next door. That's shown over here much more elegantly than my drawing, to the right, using the 3 p orbitals. There are 3 aligned p orbitals. You could say that these 2 are filled, while the other one is empty. What resonance is a way for us to understand that in certain situations, electrons are not stagnant, and thus the drawings that we draw for these cases are really not adequate in representing the full story. So what you're going to see is special arrows that we're going to use, and these arrows indicate resonance, not equilibrium. So sometimes I think students get a little lazy and you have different instances where you're drawing arrows or you think one arrow looks prettier than others. But what I want to do right now is explain the fact that arrows and the way you draw your arrows actually have a lot of meaning in organic chemistry. So resonance, which is going to be a very important retrieval cue for you guys, is when overlapping p orbitals allow electrons to move throughout overlapping areas simultaneously. What does that mean? Well, I'm going to start with these two contributors down here on the left-hand side. What I'm telling you is that this is an equilibrium arrow. It's not an equilibrium arrow, sorry. This is a resonance arrow. And what it's saying is that these two molecules are exactly the same, and it has nothing to do with symmetry. So we're going to get into this. First, let me identify arrows in organic chemistry. You're going to see reactions that go in one direction. They're irreversible reactions, and we're going to use the arrow as shown here. If I am trying to show different resonance contributors, I'm going to use the double-headed arrow. That means that the two molecules drawn on either side of the resonance arrow are the same, and they're just trying to represent some motion. The half arrows, one on top of each other in the other each direction, are reversible or equilibrium arrows. Curved arrows show the movement of electrons. So whenever you see a curved double-headed arrow, this is a double-headed arrow, it's saying take these electrons and put them here. A curved single-headed arrow, just with one barb on it, means take this one electron and put it here. And lastly, this arrow where you use two lines with the arrowhead, that's a retrosynthetic arrow, and that is actually how we show syntheses in reverse. So you can't just choose which arrow you want to use because you like the look of it. Each arrow has a very distinguished meaning to it. Okay, so let's go back to our case before here. What this is saying is that when you have an empty orbital next door, like in this particular case, I can take these two electrons from the pi bond, from the p orbitals, and move them over. Because remember, the carbon on the end, carbon 3, we'll say carbon 1, carbon 2, and carbon 3. Carbon 1, carbon 2, and carbon 3. Carbon 3, if you look on the left contributor, doesn't have an octet on the end. Remember, we just had two hydrogens. It's lacking the fourth bond. So I could kind of rob Peter to pay Paul. I can take the electrons from the pi bond and shift them over like a swinging door. So now the pi bond is between 2 and 3. Those electrons are now making up the pi bond between 2 and 3. But in doing that, I've robbed carbon 1 of the electrons. Remember, carbon 1 started with an octet. It didn't have a charge. It had two hydrogens on it that we assume. But once those electrons move over, carbon 1 is now lacking an octet and has the positive charge. So this electron density is really being distributed. The two electrons in the p orbitals are not residing solely between 1 and 2, nor are they solely residing between 2 and 3 as a pi bond. They're sort of in flux. They've got lots of rooms to go through, and they can distribute across all three atoms at the same time. This is what's called resonance. And another way to write this is, I don't usually use these resonance hybrids. I would usually write it like this. The electrons, the two electrons, basically can distribute across all three of these atoms. Atom 1, atom 2, and atom 3 with an overall plus charge across the whole system. So that's a resonance hybrid. Or you could draw it as the two contributors. The way that we'll see it the most is through the contributors. Sometimes We just draw one contributor and expect that the reader knows resonance is happening there. So resonance is very tough to convey or draw, right? How do we know it exists? Well, we know what the bond length is for given stagnant bonds. So for bonds where there's no resonance occurring, we know what those bond lengths are. So take carbon-oxygen bonds. They're roughly around 1.43 angstroms. If you look at the length of a carbon double bond oxygen, we know that those are 1.2 angstroms. So if you have a carbonate ion, which is drawn like so, I'll draw the Lewis dot structure for you. There's the carbonate, CO3, and with an overall -2 charge. Now, if you were to measure the bond lengths of the carbon-oxygen bonds for this molecule, you would neither see 1.43 angstroms, nor would you see 1.2 angstroms. You'd actually see something right in the middle. Why? Because these bonds are not really single bonds. They're actually a little bit shorter than single bonds, but they're not quite double bonds either. They're a little bit longer than double bonds. And that's because the electrons for, let's say, the negative charge, pick a lone pair on one of the oxygens, can move through resonance and give us different resonance contributors. Notice that I used curved arrows to draw the movement of the lone pair. I take that lone pair and make it a bond between the carbon and the oxygen, but in doing so, move the other pi bond up so that those electrons move up into the oxygen at the top. I could then take these electrons and move them back down and go back in the other direction. That's why resonance is backwards and forwards arrows. I could also take the electrons here and move them in and move these two out, drawing yet a third resonance contributor. So those purple electrons, that lone pair came in to form the pi bond. I still have that lone pair up here, and I now have those electrons making, overall, it's still a -2 charge. Every single one of them is a -2 charge. The only difference is the movement of the orbital, of the electrons that reside in p orbitals. Notice that I never broke a sigma bond. I only moved electrons in orbitals that were unhybridized p. So we're going to take a closer look at resonance and understand that delocalization of electrons is a good thing. So what this means is, think about electrons repelling one another, right? We spent chapter 1 talking about geometry and how electrons orient around a central body so that given that they repel one another, they have as much space away from one another as possible because they repel. So electrons exist in orbitals that span greater distances when resonance is occurring, right? Because you're taking the electrons and you're distributing the electrons over a greater area. This will minimize repulsions due to electron repulsion. Also, electrons end up spending more time closer to nuclei, right? All at once, maximizing their attractions because of all the added nuclei that it's close to as it's being delocalized over a larger area. Also, if there is a charge, Resonance also helps to stabilize that charge because, again, that charge distribution is across a greater area, a greater space. The resulting is that those charges get diminished. Having one atom bear the burden of a charge all the time versus spreading that load and having it distributed over many atoms over time is a much better advantage for the molecule and thus lowering its energy. Lowering energy makes it more stable. Okay, so in order for us to convey resonance, we have to know how to draw curved arrows appropriately. So a couple critical skills here is first we need to recognize when resonance can occur. So you guys have to get very good at understanding when resonance happens because like I said, oftentimes stagnant drawings are still used and they just expect the reader to understand resonance. Oh yeah, resonance occurs there. They're expecting you to know a lot. It's kind of like bond line structures. If the lone pair is not drawn, they expect you to know that, right? They're expecting you to be the shorthand chemist. The second thing that you're going to have to know how to do is to draw curved arrows in resonance and show their resulting contributors. So let's go over some rules first. This is rules for arrow pushing. I don't want you to break any single bonds, any sigma bonds. Okay? So that means sigma bonds or single bonds. If your arrow is coming from electrons that are involved in a sigma bond and you're moving them, that's chemistry. Chemistry is happening there. Bond making, bond breaking in that respect. You're going to change the molecule too dramatically. That is not resonance. Resonance does not change the nature of the molecule. Resonance is a thing. Resonance is something that's happening. It's not a reaction. So avoid breaking single bonds. Do not do that. That is not resonance. So this example right here is not arrow pushing due to resonance. Resonance occurs for electrons existing and only existing in overlapping p orbitals. And that is the key. You're not going to have electrons in sp2 orbitals or sp3 orbitals or sp orbitals moving. But understand that in order for resonance to occur, you're going to have overlapping orbitals that are in unhybridized p orbitals. sp3 orbitals, they never have p orbitals. Remember that sp and sp2 orbitals, when you have an atom that's hybridized sp, it has two unhybridized p orbitals. And if you have an atom that's hybridized sp2, it has one unhybridized p orbital. So those are the types of orbitals when you're more likely to find resonance. If you have a carbon that's sp3 and only sp3 orbitals, you'll never have the opportunity for resonance to occur. You need p orbitals. Rule 2, never exceed an octet for second row elements. I talked about how boron, carbon, nitrogen, oxygen, fluorine, their outer shell is shell 2. Remember, there is no 2D orbitals. Therefore, they can never, ever exceed their octet. Here are some examples of bad arrow pushing. Someone's trying to show a resonance. You take these electrons and make a new double bond between the oxygen and the carbon. Well, if you do that, carbon's going to have more than 8 electrons. Same thing here. Take these electrons and make the pi bond between oxygen and nitrogen. Well, you can't do that because nitrogen already has an octet. You can't break one of these, you can't pop one of these bonds off because remember, in resonance, I can't break a sigma bond. I also can't just oust out some electrons either. If this oxygen here, take these electrons and push them in to make a new double bond, well, I can't do that. The oxygen already has an octet, and I can't break a single bond, and I can't just shove 2 electrons out into outer space. So all of these are just bad. These are not going to ever happen. How about this arrow down here? How does this one look? Take these 2 electrons and push them in. It's kind of deceiving, right? You've got to remember your bond trends. Remember, that's a carbon at the end. That carbon doesn't have a charge associated with it. So what does that mean? Well, it means that there are 2 hydrogens there that just were not drawn. If that's the case, that carbon is an sp3 carbon, and I can't break single bonds in resonance. So this arrow is saying take these 2 electrons and make a double bond between the carbon and the oxygen. Well, I can't do that. I can't exceed the octet. I can't make this bond if I don't break something else, and I can't break single bonds, so I'm stuck. So this is not good. Not good. This is another bad arrow. Okay. Number 3, second row elements will rarely, but sometimes, have less than their octet. So if you'll notice, this arrow is okay. If I take this pi bond, so take the 2 electrons that make up the pi bond and pull them out of being the double bond and shove them into the oxygen. So now they act as a lone pair. I took them from a bond and pushed them into the oxygen, making it a lone pair. Everybody's okay, right? The oxygen started with an octet, and it still has an octet, albeit now it's outside of its bond trend. The oxygen now bears a negative charge because it has a lone pair instead of a second bond. But we're still okay because oxygen is fine with its octet. The carbon, on the other hand, had an octet, and then by taking the electrons and shoving them away into the oxygen, it left the carbon without a 4th bond, making it positively charged. This carbon now does not have an octet, but we've seen carbons with a positive charge before. So we're at least, well within the rules of this happening. So this can occur. However, of the 2 contributors, which one do you think is the more stable one? The fully neutral one where everyone has an octet, or the contributor on the right that has 1 less octet and really 2 charged atoms? You guessed it. This is probably the better contributor of the resonance that could possibly occur. How about we draw resonance for the molecule shown below? I'm going to redraw it as a Lewis dot structure. Ooh, wait, I've exceeded. Can't have 2 lone pairs. It's got 3 bonds and 1 lone pair. Remember, I can't exceed the octet. So one of the lone pairs must be because it's sharing the electrons rather than having the lone pair all to itself. A resonance contributor for this, the only thing I can break, let's see, I can't take the lone pair and make a triple bond because I can't break any carbon sigma bonds. So the only way to go is to take a pi bond and shove it into the oxygen. This tends to make sense. What you'll notice is that resonance, when there's a dipole, resonance tends to go in one direction. So if you have a polar bond, the resonance arrow tends to go towards the more electronegative atom. And this makes sense. So we still have the sigma framework. Didn't break any of these bonds. But I shoved the lone pair into the oxygen. So now look at that. The oxygen is in its bond trend again, so it's no longer plus charged. But you know what is plus charged? The carbon. Because the carbon lost that bond, lost those electrons completely over to the oxygen. So now the carbon is without an octet. So of these 2 contributors, which one do you think is the more abundant contributor? You could say, oh, well, oxygen being positive, that's not good. Someone could say, well, carbon's positive and doesn't have an octet. Which one wins out? Well, if you think about it, I know the oxygen with a positive charge might look a little uncomfortable to you because you might rationalize oxygen's electronegative and it doesn't want to be positive, which is absolutely true. However, of these two, the contributor on the left, if you look at every single atom, all of them have octets. If you look at the atoms on the right, the carbon does not have an octet, and that wins out. So of these two, we're going to draw it like this contributor more often than not because it's the one that is more stable among the two. So when you're using curved arrows to show resonance, you often have to make sure that charges are implicit when necessary. Okay, so don't forget about the charges. What's interesting here is that charge, you can think about that old rule in Gen Chem, you can't create or destroy matter. Well, think about it with respect to electrons and charge. All I'm doing is moving things around. If my contributor on the left had a positive charge, there should be an overall positive charge on my contributor on the right. And that's indeed the case, right? Oxygen positive to carbon positive. Positive charge is maintained across contributors. So the overall charge of one contributor should match the overall charge of every other contributor. So make sure that you're making sure of that. Let's look at the arrow pushing for the resonance in the brackets. We're asked to draw the resonance contributor indicated by the arrows. So the arrows tell the story, okay? So the story is, and again, I can draw all of these out without breaking any single bonds. So I'm going to draw the single bond framework because that's not going to change. It can't change. What this is saying is, okay, these electrons didn't get touched, but the electrons right on the left here, they're taking those two electrons and they're making a pi bond with them right here. And as that bond is being formed, the pi bond on the right is getting dumped into, it's breaking, being taken away and getting dumped into the carbon at the bend. All right. Let's figure out what's going on here. I'm not done with this structure. Overall, I started with a neutral molecule. If you look at the contributor on the right, things are not in their normal bond trend. The oxygen at the top has 3 bonds in a lone pair. That means it's positively charged. The carbon down at the bottom here with the lone pair, carbon usually has bonds. It usually shares. It never really has electrons of its own. So this makes the carbon negative. Overall, if you look at the overall charge for the contributor on the right, it too is formal charge overall neutral. So make sure that your charges align. The fact that you started with an overall neutral molecule, you should end with an overall neutral molecule. If you forgot to put the negative charge and only had the positive, you'd be like neutral to positive. That, if it's just resonance, that can't be the case. So are any of the rules violated by doing this shift? And the answer is no. I only use lone pairs and pi bonds. Did we account for formal charges on the contributors? Absolutely. We checked to make sure that we didn't create or destroy any charges in the process. Okay, so that's how we can follow along with arrow pushing. And these arrows are showing us the story of how to go from one contributor to the other. But how do we recognize resonance? How do we recognize when resonance is a thing, especially when they only give us one stagnant drawing? Well, there are 5 main bonding patterns that I'm going to go over with you so that it'll be a lot easier to predict when resonance occurs. Now, some of these terms are new and we'll go over, don't worry, this is just a summation page. The first one is allylic lone pairs. Then we'll talk about allylic charges, positive charges. Lone pairs of electrons adjacent to a positive charge. a pi bond between two atoms with different electronegativities, and conjugated pi bonds in a ring. So let's look at this case right down here. Draw the resonance contributor and curved arrows for the following. So what does this mean? Well, it's saying that we have a lone pair on that carbon because that carbon has a negative charge on it. That's what the drawing says. And I know a carbon with a negative charge has a lone pair that it normally doesn't have. I can use that lone pair starting from the negative, take that lone pair and dump it right between the two carbons. Now I know that that carbon has an octet, but I can break pi bonds. Remember, not sigma bonds, but I can break pi bonds and dump that pi bond electrons into the carbon on the far end. Let's redraw this and see where it gets us. So what I did is I used the lone pair to make this new pi bond, and I took the two electrons from the pi bond at the bottom, I removed them from the bond and plugged them into the carbon adjacent. These are the two resonance contributors for the molecule indicated. Now we're going to go over these rules, how to recognize patterns, but to do so I have to define a few terms that we're going to be seeing a lot. The first one is called vinyl, and the second is called allyl. Vinyl means directly on a pi bond, or in this case, a double bond. Allyl, or allylic, means one atom away from, one atom next door. So if I have a carbon-carbon double bond, like in this first case here, notice that the two carbons involved in the carbon-carbon double bond are the vinyl positions. So anything off of those carbons would be called a vinyl fill in the blank. If I had some sort of system, a hydrogen, a chlorine, something, off of a carbon next door to a double bond, then it would be considered allylic or allyl position. So I could take my vinylic, right? I can find, these are all the vinylic positions. Okay, vinylic positions. So that means that this chlorine is vinyl and this chlorine is vinyl. I can then look at the allylic positions. So I want to look at all the carbons next door to the double bond. That's next door, that's next door, that's next door. I've highlighted the allylic positions. Therefore, this is an allylic chloride, an allylic chloride. Oh, and there's just hydrogens on the other one. The chlorine far to the right is just a regular alkyl chloride. It's not on a vinyl position, it's not on an allylic position. So the first one is whenever you have a lone pair on an allylic position, that lone pair can participate in resonance. So circle all the allylic lone pairs. So you've got the double bond. So if you find a lone pair on a carbon next door to a double bond, or on an atom next door to a double bond, you're good. Double bond, carbon with a lone pair. Double bond, atom next door has a lone pair. Double bond, atom next door has lone pairs. Double bond, ooh, look. In these two cases, it's not a regular carbon-carbon double bond, but just any pi bond. Pi bond, next door, the atom has a lone pair. Pi bond, next door, the atom has a lone pair. That means for every single one of these cases, that lone pair can push in and form resonance contributors. Let's draw those resonance contributors. Take the lone pair, push it in to make a new bond, break the p bond or the pi bond, and dump the electrons at the end. Okay, let's do it again. Take the electrons from the allylic position, dump them to make a bond, break the bond, and dump them into the end. Check your charges. Take the lone pair, dump them in, break the pi bond, dump it into the atom at the end. Check your charges. Now remember, there were already 2 lone pairs up there. Those are still there, giving us an overall negative oxygen. Take the lone pair, dump it in, break the pi bond, pushes it up to the nitrogen. New pi bond there. Now the nitrogen did have a lone pair, which is still there, but we dumped the extra lone pair in. That nitrogen has now a negative charge, right? Overall negative ends overall negative. Last one, take that lone pair, right? Dump it in to make a pi bond, break the pi bond, and dump that up into the oxygen. Again, the oxygen did start with 2 lone pairs. The oxygen ends with an extra lone pair, giving it a negative charge. The nitrogen is now out of its bond trend. It used its lone pair. So now it has 4 bonds. It lost some electron density that it once had all to itself. So these are the resonance contributors for all of the properly drawn arrow pushing that show resonance between each of those systems. So resonance is a weird thing, right? If you look at one of these molecules, you could draw it one way or the other. It means the same thing. It's like trying to describe something using a stagnant image, right? It's like trying to draw a runner, right? If someone in real life, they're running, and you're just trying to convey that the runner is running, you and I can look at the picture and go, oh yeah, that person is running. Do we actually see them running in motion? No, but the image is enough for us as, growing up and looking at a picture of someone running. We understand that what's going on in the picture is happening, even though I'm only looking at a still frame of it, if that makes sense. Resonance is the same way. You need to understand, you need to see that stagnant image is really this runner. And what really is happening, if you weren't looking at a stagnant image, what's really happening is that the electrons are neither here nor there. They're somewhere in between. They're sort of spread out over these atoms. They're distributed, and the arrow is showing where they're distributed. Allylic positive charges are also areas to be aware of, because we could have a pi bond with a positive charge at the allylic position. So if you look, what we just saw up here, we just saw an allylic negative charge. And we saw that those electrons can dump in and be resonance stabilized. You could also have an allylic positive charge. Effectively, positive or negative, it's a p orbital that is able to accept or donate electrons with a pi bond next door. So it doesn't matter, positive or negative, if you have an allylic position with a charge on it, it can resonate. That's the bottom line. So I can draw, instead of having the lone pair going towards the pi bond, in this case, because it's a positive charge, I'm going to take the pi bond and fill it. This gives me the pi bond in a new position and a positive charge over on the other side. It's like a swinging door, backwards and forwards, but really, as I showed you the resonance hybrid, it's like distributed, I don't know, those electrons are somewhere between these three atoms with an overall positive charge. If there are multiple pi bonds, then multiple contributors are possible. Let's take it one step at a time. I could take the pi bond, and you see that there's a charge at the allylic position. I take the pi bond and I move it across. Let's draw the result of that story. Right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Notice that the arrow is just saying take the electrons between 2 and 3 and move them over to 1. Now where's the positive charge? Think of it this way. A positive charge means emptiness for a carbon, right? A positive charge on a carbon means it's lacking an octet. So you're taking these electrons, like it's like taking gravel and filling the hole. But if you're taking gravel from between 2 and 3, the hole moves. So now if you're filling the hole, so that 1 is now filled, 3 now has the hole because you've shifted the electrons over. So the empty hole is now at 3. I could keep going. I could take the 4, 5 pi electrons and shift them over and fill that 3 hole. But now 5 is going to be the empty hole. One, 2, 3, 4, 5, 6. There's actually some more resonance contributors to this because remember, these bonds are not really single bonds and they're not really double bonds. Every single bond, because it's in flux like this, it has rotation. Even though it looks kind of like a double bond, there's still rotation as I showed you. And so let's just say that we rotated 3 and 4 before we even, finished. Understand that if I rotate around 3 and 4, one, 2, 3. I'm rotating now around 3 and 4. And then we have, oops, I drew this kind of incorrectly. So I've rotated. And now, when you shift over, and then you shift again, what you're seeing is changing of the double bonds. The double bonds are not trans or opposed to one another anymore. You're starting to get cis double bonds. Okay, as I've written this double bond right here is trans. Look at the vinyl positions. Vinyl positions. Notice that carbon 2 and carbon 5 are opposite to one another. That's trans. If I look at the vinyl positions of a cis position, the 2 carbons are on the same side. We'll talk more about this in the future, but what I want you to be aware of is that as you're shifting between contributors, there's actually the opportunity for rotation in between all of that mess. And you are going to get all of the double bonds isomerizing or changing through the process of resonance. And that makes for a lot more resonance contributors than you thought possible. 1, 2, 3, 4, 5, 6. I could say all of these atoms are in resonance with some positive charge. That's how I would draw the resonance hybrid for this molecule. A lone pair adjacent to a positive charge, as we just shown, could also come from a negatively charged atom. So explain how the formal charges are affected by the electron movement in the following examples. So if you look here, I typically like to think about moving electrons towards the more electronegative atom, or if you can do it, start your pencil or pen on the negative charged atom. The negative charged atom usually has lone pairs, and you want to move from high electron density to lower electron density, from negative to positive. That's the trend. So if I look here and you don't know where to start with the negative charged species, the lone pair, and then move it towards the area of less electron density. So when we draw the resonance contributor here, you're going to see this. That's a much better electron resonance contributor. It's neutral, everyone's in its bond trend, and everyone's octet is met. We could also draw down here what happens when you push the electrons as indicated. Take those two electrons and make a double bond. There still remains a lone pair on the oxygen. Now, the carbon that we started with had only one hydrogen. That's why it has a positive charge. It still only has one hydrogen. But now that carbon has an octet and is much happier, no longer charged. The oxygen is outside of its bond trend. It had to use up one of its lone pairs, and so the positive charge now resides on the oxygen. Which of the two contributors is probably the more stable one? This one. Why? Everyone has an octet and is happy, despite the oxygen positive charge. Lone pairs adjacent to positive charges. Again, we can see this with a nitrate example. In this case, again, we can't just show one arrow. In the previous case, notice how one arrow was suffice to clear everything. Move those electrons into the hole, move those electrons into the hole. And I only had to draw one electron arrow pushing to get to the resonance contributor. Sometimes that's just not enough. In the nitrate case, if I start with, where do I begin? Well, start with the area of increased electron density. That would be the oxygen with the negative charge. Take one of those lone pairs and push it into the nitrogen. Now, you remember the bad arrow example? You'd say, well, you can't push it into the nitrogen because the nitrogen has an octet. And you're right, it does have an octet. But if the atom you're pushing into can make room without using sigma bonds to break, so remember, you can only break pi bonds. If that's still an option, then you can push into an octet atom. So I take the area of more electron density, take those electrons, push them in to make a new pi bond, but I'm just going to shift over the old pi bond on the other side and dump those into the oxygen. So this is perfectly fine for a nitrate. New double bond. That lone pair is now on the oxygen. Remember, that lone pair is now part of the pi bond. So these are resonance contributors for nitrate. And if you look from one to the other, the nitrogen still has a positive charge. The oxygen negativity shifted from one oxygen to the other. So the delocalization of the electron density is distributed across 3 atoms. These are equal contributors because there's really no difference between one or the other. A pi bond between atoms of different electronegativities will shift the electron density towards the more electronegative atom. For instance, let's consider A. Notice that the direction of the electrons, the pi bond, we've seen this one already, the pi bond breaks and the electrons can get pushed into the oxygen. This is perfectly okay, even though one contributor is way lower in energy and more stable than the other, because it's neutral and everyone has an octet. Let's contrast that to example D, where the electrons are being shown going from and away from the oxygen. And this is because when you're drawing resonance contributors, they should align, the charges that form should align with the dipole of because the two atoms have differences in electronegativity. Notice that the oxygen being more electronegative, the carbon being more electropositive. Notice that the flow of electrons in resonance, it actually was in agreement with the dipole. Here, the dipole is still carbon partial positive to oxygen partial negative, and I drew the electrons going from the pi bond into the carbon, kind of against the grain, if you will, of the flow of the dipole. So this is not ever going to happen. You're never going to be forming that, an octetless oxygen. No way. That is not going to happen. Scribble that one right out. No, 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 no. Okay, it didn't move with the dipole. Can we move these electrons down into the carbon in case B? No. Why? The dipole is going in the other direction. And carbon has an octet, and I can't break anything to make way for a third bond. So that is not the way that it's going to go. If I drew a resonance contributor for this, it could only move in one direction, and the only direction it can move is towards the more electronegative atom. And that's what this rule is all about. Take those two electrons and dump them into the nitrogen. Nitrogen is now outside of its bond trend, and so it's got a negative charge on it. And there must be another charge because the molecule started neutral. Well, I did rob the carbon. The carbon no longer has an octet, so it must have a positive charge. That is a perfectly agreeable contributor to resonance, but it's just not the more stable one. This is indeed the more stable one because everything's neutral and everyone has an octet. Now, alkenes, carbon-carbon double bonds, don't have a difference in electronegativity, and so there's really no resonance contributor in one direction or the other. So we don't really write a resonance contributor for just a carbon-carbon alkene without some electronegativity pulling it in one direction. Lastly, we have pi bonds in rings. Now, despite being carbon-carbon double bonds, if they're in a cyclic fashion and they can free flowly around and around, we will see things like benzene having massive amounts of resonance. This is such a stable factor that we have a whole chapter dedicated to it. So each atom in the ring must have an unhybridized p orbital that can overlap with its neighbors. And if you'll see, I can go ring around the rosy with these just using the p electrons. And it doesn't really matter how you draw a benzene ring. In fact, it doesn't matter so much that most of the time we just draw it like a resonance hybrid. Just the 6 electrons that make up the pi system are just round and round and round. Arrows can be shown to move clockwise or counterclockwise. It really doesn't matter. What the hybridization is on each one of those carbon atoms, calculate it. They're sp2. They have hydrogens that you just don't see. They're all sp2. That means they all have a beautiful, here's the sigma framework, they all have a p orbital You could say, oh, there's the pi bond, there's the pi bond, there's the pi bond. But really, are those pi bonds stagnant? No, pi bond could be anywhere. So really, it's just round and round and round and round and round. Hence the resonance hybrid we draw. Okay, this is the summary slide of what we just looked at, those 5 rules. How you identify when there's resonance, even though we're not telling you or saying so, we're just assuming you're an awesome chemist, and you can identify resonance patterns. First one, find an allylic position that has lone pairs. Second, find an allylic position that has a charge. Third, find a charge with a lone pair next door. Fourth, find a pi bond between 2 atoms that have differences in electronegativity. And fifth, find a ring that has alternating pi systems. Now, for this example down below, I'd like you to show all of the resonance contributors for the molecule. I'm going to let you guys practice this one on your own. Okay, I've already discussed most of this with you, but I'm going to go over it again. How do we look at the different resonance contributors and understand the stability? Number 1, formal charges generally decrease stability, especially a positive 1 charge on an electronegative atom or a negative charge on a low electronegativity atom. And 2, complete octets increase stability. I've already showed you examples of this. I'll give you an example just to demonstrate one more time. If I started with this molecule and said, okay, let's draw the resonance contributors for it, we would say, let's take the allylic lone pair and push it towards the positive oxygen, breaking only pi bonds. I'm only using lone pairs and pi bonds. Do not use the sigma framework. You can very easily draw the sigma framework without bother. Okay, I made a new bond between the oxygen and the carbon, and I dumped the pi bond electrons into the oxygen at the top. Let's assess the charges. The oxygen at the top is now neutral. The oxygen at the bottom is now positive. Okay. Another resonance contributor could have been, oh, well, I could have just taken these pi electrons and moved them into the oxygen. This gives me a better oxygen because now it meets its bond trend, but the carbon is now positively charged. Notice that overall each one is positively charged, but they are different contributors. Of these, the worst contributor of them all is this last one. Why? Because the carbon doesn't have an octet. So it violates that second rule. Now, you've heard me use a few terms, and sometimes it gets a little confusing. People are like, well, what's the difference? Does she mean the same thing? I don't get it. So I'm using the word resonance. Resonance is something that happens when you have one of those 5 situations we just discussed. Okay, resonance can occur. Resonance, effectively, is when electrons in p orbitals are delocalized, right? Distributed across many atoms. This delocalization, which is resonance, increases stability because you're lending more surface area to the electrons, and so they're not repelling one another. So electrons not in resonance are considered localized. Electrons in resonance are considered delocalized. Resonance and delocalized electrons are really the same thing. they improve your stability. So in summary, electrons exist in unhybridized p orbitals that overlap with other p orbitals on neighboring atoms. That is what resonance delocalization is. So delocalized electrons must be in sp or sp2 hybridized atoms and can never happen on sp3 carbons. Never on an sp3 carbon. So what is the hybridization of this nitrogen atom? If you were just finishing chapter 1 and I asked you for the hybridization of the nitrogen atom, you would tell me, fresh out of chapter 1, you'd say it has 4 electron domains. So therefore it has to be sp3 tetrahedral. And then I would say, now after chapter 2, I'd say that answer is wrong. What? Why is that the case? Well, we just learned about electrons that look stagnantly there but aren't, because that lone pair is allylic to a pi bond. I know that that lone pair can resonate. If that lone pair can resonate, that can't be in an sp3 orbital. Remember that now the oxygen's negative, the nitrogen's positive. Now what would you say the nitrogen's hybridization is? Well, it has 3. It's got a double bond, that's 1 electron domain, and it has 2 single bonds. So it has 3 electron cloud domains. That puts it at sp2 trigonal planar. And that makes more sense because sp2, each one of the sigma bonds is an sp2 orbital overlap, and the pi bond, you must have an unhybridized p orbital. So if resonance is going to occur, you have to have those electrons in an unhybridized p orbital. You need that. It can't be in an sp3. So after what we just learned from chapter 2, when you go back now, you guys have a much more mature way of looking at this. If I ask you for the hybridization and ultimate geometry around a given atom, yes, follow chapter 1. But do a second check. If that atom has a lone pair and that lone pair can resonate, then you've got to reconsider. You're going to consider probably an sp2. You take it down by 1. Say, nope, not sp3, must be sp2. Okay? And here's an example of, say, triethylamine. Okay? If I asked you for the hybridization of that nitrogen, you would say, well, it's got 4 electron clouds. Oh, one of them's a lone pair. Can that lone pair resonate? Is it allylic? Does it have a charge next door? No. So there's no resonance for that nitrogen. So it does indeed have 4 electron cloud domains, making it sp3 tetrahedral. I'm going to bring this back to the first slides of this chapter. This is an amine. An amine does not typically, but as drawn, this amine has no resonance delocalization of that lone pair. From a chemical standpoint, how it behaves is very different than the functional group up above, which if you learned them already, is not an amine, it's an amide because it has a carbonyl next door. There's resonance distribution of that electron density. That is a game changer in how these two molecules behave functionally. So you've got to understand, and we're starting to build the case for why these functional groups are indeed different. Here's a better pictorial of the unhybridized p orbitals sharing electrons, right, through those kissing p orbitals that are parallel, showing that there's distribution or delocalization of that lone pair. Now, lone pairs adjacent to a double bond are capable of resonance, but vinyl lone pairs are typically not able to resonate. Why is that the case? Let me just draw this molecule out for you again. Okay, so understand that if I had this ring, I'm going to draw just the sigma framework with the nitrogen right here. Okay, those are the sigma bonds. Okay, there's hydrogen, 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 and hydrogen. Okay, every single one of these has a p orbital. Okay, so understand that those pi bonds, right, that I'm drawing in red here, those are because they're electrons shared between two adjacent unhybridized p orbitals. Now, the nitrogen, in this case, that nitrogen, right, has the 3 bonds and a lone pair. Now, I didn't draw the lone pair. All I've done is drawn the 3 bonds that nitrogen has, and I didn't draw that lone pair yet. Notice that the p orbital of the nitrogen is already full. It has a p orbital that is playing in the resonance game around and around the ring, and that is the red electrons, because the nitrogen has a p orbital and it's in the y direction, and it is distributing those electrons around and around. So where are the lone pair? Well, the lone pair is not in a p orbital. The lone pair is in the z plane, and it's out of the game. In order for electrons to resonate, they must be in p orbitals that are aligned. So if you have orbital, 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 p orbitals, yeah, they can like pass the potato across one another. But if you had an orbital with a lone pair in it on the same atom that was orthogonal, 90 degrees to the game, lying down on the ground, you can't pass the ball to him. He's not even in the game. All of the orbitals that share in resonance have to be in the same plane, aligned with one another. If you have one 90 degrees, it can't catch the ball. It can't share the electrons. It can't overlap in a parallel fashion. So because the nitrogen already has is vinylic, it's a vinyl nitrogen. It's not allylic, it's vinyl. That's why the terms allylic and vinylic, and your ability to distinguish the difference, this nitrogen here is vinylic. That is a vinylic lone pair, not technically an allylic. I know it's next door to a double bond, but the vinylic side of it wins out. You can't have a lone pair both vinylic and allylic at the same time. The vinylic one being that it's on that same, the orbital has to be misaligned. So where are the delocalized electrons? Here's another image, much better drawing than me. You can see the nitrogen on the right. It's already got a p orbital that's playing in the game. That orbital's already filled with 2 electrons, and so therefore the lone pair sits in an sp2 hybridized orbital on the outskirts, orthogonal. The nitrogen's lone pair is positioned orthogonal to the plane where the other pi electrons reside. Thus, resonance for the lone pair does not exist. Now I want you to think about the amide again. The amide functional group is neutral. The amine is basic. Why? The nitrogen can use its lone pair whenever the heck it wants and do chemistry with it. The amide cannot. The amide's lone pair is tied up in resonance, and it doesn't fully own that lone pair. It's kind of distributed and shared. So it doesn't do the same acid-base chemistry that an amine can do. Pyridine, on the other hand, is actually an amine base. And what's nice about it is that that lone pair, as I showed you right down here below, it is not in resonance. So that nitrogen, despite that lone pair looking like, oh, it could be maybe in resonance, it's not. And so that lone pair acts like a base and can do acid-base chemistry because it does not have to share that lone pair with anything in the ring. So pyridine is actually a pretty decent base. I have remaining resonance practice for you. You can label each of the atoms and below with their hybridization and give the bond angles around each of those atoms you would predict. I'd like you to reflect, now that we've reached the end of Chapter 2, on the retrieval cues that we've defined, and think about your skill level for each of the following: being able to identify functional groups, drawing bond line structures, recognizing when resonance can occur, and drawing curved arrows to show different resonance contributors. The remainder of this chapter notes show different resonance practice, another practice problem for molecular formula, drawing bond line structures to test your ability, and also filling in formal charges for when things are not in their formal bond trend, and also filling in any necessary lone pairs when charges are given. So outside of bond trends, what's missing from a lone pair perspective.